All right, welcome everyone. Today we're going to start to look at a relationship between, or a way of converting between a line integral and our double integral that we kind of talked about in the previous chapter. Okay, because sometimes as we start to work on some of these integrals, dealing with the boundary, or kind of having multiple multiple expressions to use for our boundaries, okay, or for our curve that we're going to form this line integral on, it might be easier just thinking about the area enclosed, and that's what this theorem, thankfully, kind of identifies this relationship between. Okay, so let's start to go through the document and we'll discuss. All right, so here we go. Let me zoom in here. All right, so we're going to talk about Green's theorem. And so what Green's theorem does is that Green's theorem relates, or in some respect rewrites, a line integral around a closed path, okay, to a double integral over the region enclosed by the closed path. So we can imagine, we'll look at it in 2D here. All right, but suppose we have some path, C, and we say this oriented positively, going around that curve, that path, the initial point and terminal point the same, going in the counterclockwise direction. That's this positive orientation. Meaning as we start to kind of think about this R of T that we're going to traverse, we're going to go around that path in the counterclockwise direction. Okay. And then we kind of think about like how we label our quadrants, how we kind of cycle through our angles in polar form, right? Counterclockwise, and that kind of identification, that thought, right? But we have this closed path. We're going around counterclockwise, okay? And so we start to see, with some of these closed paths, we start to use this little circle, little open dot on the integral, and we have this idea, okay, we're going across that path, this closed path, positively oriented, okay? And we have some function p dx plus q dy, this kind of line integral that we would have managed in 16.1, the beginning of this chapter, okay? But depending on that curve, depending on that r of t, it may be difficult to parameterize, or as we'll see in an example work on it, might have like multiple equations we have to kind of separate for that curve, right? We're using different expressions depending on our parameter that we have to separate that integral. So instead of having to manage that parameterization, working with that curve, what we can do instead is that we can equate this. If I think about it, if I can identify in some way this region enclosed, we can equate that to this integral over the region, d, but in that conversion, since we're switching from a line integral to a double integral, this kind of area integral, if you will, we're going to look at dq dx, the partial of q, with respect to x minus dp, sorry, that solid p, the partial p with respect to y, that difference, dA. Okay, where C is a pathway, and then D is our region enclosed. So we're going to be able to equate. So if we can better equip ourselves, going back to our discussion with double integrals in the previous chapter, right? Separating that region out. What does X range through? What does Y range through? We can even convert this to polar if we needed to, but most often be dx dy, dy dx. We start to incorporate that information. Okay, so this theorem gives us our way of rewriting. Okay, and so let me get to the formal statement, and then we'll do some examples. Okay. Greenspan says here, let C be a positively oriented piecewise smooth, right? So for these different spaces, it's a smooth pair of continuous, no sharp turns. We're expecting continuous first derivatives, simple, closed curve, simple. It doesn't loop upon itself. It doesn't make like a curlicue, right? It's not like a cardioid or one of our rose petaled curves in polar. Okay, it doesn't cross itself. It's closed, right? Closed curve in the plane, whether it'll be the most common XY plane, but it could be in the YZ plane, XZ plane. And we're going to let D be the region bounded by that closed curve C. Now if P and Q, these functions in our line integral, have continuous partial derivatives, on an open region that contains D, right? Making sure that interior of our space, there's no points where these partials are going to be undefined, have asymptotes, have holes, right? Even interior that space, our partials are continuous, okay? Then, and as I had written up, we're able to take that line integral, this function working in x direction, this function working in y direction, okay? Along that path C, we're going to rewrite it as this double integral over that region D enclosed of the partial q with respect to x, take away the partial p with respect to y, dA. Okay, and so some notation here, and we'll look at an example. All right, since C is the boundary of that region, of that closed space D, sometimes we can rewrite C as this kind of looks like a partial of D. And this is just, again, boundary curve for that region D. So you might start to see that in our notation, that in our problem. Okay, just making sure I cover this. In terms of that work, okay? All right, let's look at this example though. And so depending on our region, we can actually go back and forth. Sometimes we might have a double integral. It may be easier to compute it, evaluate it as a line integral, right? When we have those kind of identification, I'm not sure exactly how I would separate that region out. If I can build those equations for the boundary, it may be beneficial to evaluate in that regard, okay? All right, so with that said, let's look at an example though of using Green's theorem. Take this off. For example, let's borrow this problem. Check out number 6. This is on page 1142 from our text. Use Green's theorem to evaluate the line integral and we have here this integral over the path c, x squared plus y squared dx plus x squared minus y squared dy. So when we look at these types of problems, we're asked to use a particular theorem, okay? And I mean, I forgot to explain what C is first, sorry about that. So C is the triangle with vertices, right? A common region we think about 0, 0, the origin, the point 2, 1, and the point 0, 1. There we go. Okay. So if we start to think about that curve C, right? Starting at the origin, 0, 0. Then we go to 2, 1. Then from 2, 1, we go to x is 0, y is 1. And if we have a full triangle, we need to make sure we close that down like so. All right, so there's our path C, the boundary, right? C are the sides of the triangle, right? So if we were looking at this line integral and computing it as distinctly a line integral, I'll say as this kind of pure line integral, handling it in that manner, we would need to define that curve C explicitly along each side of the triangle, right? We'd have to imagine taking C1, C2, C3, right? That integral we would have to transform as the sum of those three sides. I'm gonna put a little dot, dot, dot. The expression the function that we're evaluating is the same, but we're going to think about then our parameterization, right? For R1, what does that look like? For R2, what does that look like? R3, what does that look like? And then x of t, y of t, for each of those, thinking about how we're going to rewrite these functions in terms of x and y of t, getting those integrating factors, the dx, in terms of dt's, right? Not impossible, time consuming. So instead, with that closed region, seeing that as a region in which to integrate will be a lot easier, okay? So over here, Green's theorem, instead of having to separate into those three different boundary lines, it allows us to consider, to compute the line integral as a double integral. Okay, that setup, as long as we can identify that region D, take the partial Q with respect to X, partial P with respect to Y, P, A. And so, drawing that again rather quickly, 0, 0, 2, 1, 0, 1, right, are three vertices of that triangle. But now we have this region D. And depending on how we want to organize that dA, we can rewrite as either dx dy or dy dx, depending on how you want to organize it. In this case, again, out of common habit, we go vertically in that regard. X goes between 0 and 2. Y, this is y equals 1 up here. That's the height of it. Down below, this line passes through the origin. Its slope, it goes up 1 over 2. Sounds like y equals 1/2 x. So it goes from that line, 1/2 x, up to 1. We could also go horizontal slices. Y goes from 0 to 1. X goes from 0 out to this line. X equals 2 times y, so 2y down. Depending on which way you want to organize, okay? But that's if you go horizontally, okay? Thinking about that from our double integrals. So instead of having to separate those different spaces, now we just have one solid region, and we can identify these limits of integration. But now let's think about our function, right? So our integral, our P and Q that is, was x squared plus y squared dx, x squared minus y squared dy, right? So in this case, our function for P, x squared plus y squared, push this up a little bit, dp, dy, right? Kind of the opposite variable to y, q, x squared minus y squared, dq dx to x. So this becomes this double integral over the region D of dq dx to x minus, so it starts off with a subtraction, dp dy, 2y, dA. And the way we had talked about up here, depending which organization we might find easier, I think out of habit I'm used to doing the x on the outside, 0, 2, y interior, but again, it doesn't necessarily matter. If we're going from x to 0, 2, y is going to go from 1/2 x to 1, okay? And so evaluating, again, a big part of it is just that setup, hopefully from here, with the practice we had done before, evaluating our double integrals. Not too terrible. 0, 2, integrating with respect to y here. Let's do it in green. 2xy minus y squared from 1 to 1/2 x. We still have that dy hanging on, or that dx, pardon me, hanging on. We did our dy integral first. Integral from 0, 2, plugging in y is 1, 2x minus 1, plugging in that 1/2 x, 2x times 1/2 x, 2 times a half is 1, x times x squared, minus 1/2 x squared, sounds like a fourth x squared dx. A little bit of rearranging. X squared minus 1/4 x squared, 3/4 with a negative up front, negative 3/4 x squared plus 2x minus 1, dropping the parentheses, combine my like terms, keeping the dx okay. And then now evaluating, this is like our first semester calculus, polynomial integral, negative, right, 3/4, the antiderivative, the integral of x squared, 1/3 x cubed, the 3's cancel, so it's minus 1/4 x cubed plus x squared minus x. Evaluate 2 and 0. The 0 we know goes away. Plugging in that 2, we get negative 1/4 times 2 cubed is 8 plus 4, 2 squared, right, minus 2. Negative 2 plus 4 is 2 minus 2. I'm getting 0. Look at that. Double check my integrals. But on that closed path, we're getting that 0. Okay. And so had we gone through that line integral, or that set of line integrals, gone through all those calculations, we would have seen that each of those, in the end, would balance it out, cancel each other out. We would have gotten that 0 result there as well. Okay. All right. And so the real work is going to be, as we go through, thinking about that closed boundary and converting to that double integral. Okay. But depending, there are going to be some instances when it may be easier, instead of a double integral, finding an integral of that closed region, it may be easy to think about the boundary. Okay. Create that parameterization for a boundary or multiple boundary lines and evaluate those line integrals. That could be supported. Okay. But working through rewriting, converting that line integral to our double integral. Okay, so let me stop there. I think I have some other examples on the Canvas page to look at, to work through. to support that conversion, okay?